Distinguished future physicians, welcome to Stomp on Step 1, the only free video series that helps you study more efficiently by focusing on the highest yield material. I'm Brian McDaniel, and I will be your guide on this journey through the null hypothesis, alternative hypothesis, type 1 and type 2 error, p-value, alpha, beta, power, and statistical significance. This is the 11th video in my playlist covering all of biostats and epidemiology for the USMLE Step 1 Medical Board exam. There's a lot to cover, but we will try to move through things quickly and break them down into bite-sized pieces. We will start with the null hypothesis, which is represented by H subscript 0. The null hypothesis states that there is no difference between the groups being studied. In other words, there is no relationship between the risk factor or treatment being studied and the occurrence of the health outcomes. For example, if we are comparing a placebo group to a group receiving a new diabetes medication, then the null hypothesis states that the blood sugar or medical complications would be roughly the same in each group. We will talk about this more in a second, but by default, you assume the null hypothesis is correct until you have enough evidence to support rejecting this hypothesis. If you are a researcher, it's usually kind of a bummer when the null hypothesis is valid because it means you didn't find a treatment that works, or that the risk factor you're studying isn't as important as you were hoping. The alternative hypothesis is denoted by H subscript A or H1. As you might expect, it is the opposite of the null hypothesis. This hypothesis states that there is a difference between groups. The research groups are different with regard to what is being studied. In other words, there is a relationship between the risk factor or treatment and the occurrence of health outcomes. Obviously, the researcher wants the alternative hypothesis to be true. If HA is true, it means they discovered a treatment that improves patient outcomes or identified a risk factor that is important in the development of a health outcome. However, you never prove the alternative hypothesis is true. You can only reject a hypothesis, say it is false, or fail to reject a hypothesis, which means it could be true, but you can never totally be sure. So a researcher really wants to reject the null hypothesis because that is as close as they can get to proving the alternative hypothesis is true. In other words, you can't prove a given treatment caused a change in outcomes, but you can show that that conclusion is valid by showing the opposite hypothesis, or the null hypothesis, is highly improbable given your data. Anytime you reject a hypothesis, there is a chance that you made a mistake. This would mean you rejected a hypothesis that is true or failed to reject a hypothesis that is false. Type 1 error is when you incorrectly reject the null hypothesis. The researcher says there is a difference between groups when there really isn't. It can be thought of as a false positive study result. Usually, we focus on the null hypothesis and type 1 error because the researchers want to show a difference between groups. If there is any intentional or unintentional bias, it is more likely to exaggerate the difference between groups based on this desire. The probability of making a type 1 error is called alpha. You can remember this by thinking that alpha is the first letter in the Greek alphabet, so it goes with type 1 error. I'm going to hold off on talking about alpha and p-value for a few slides. Type 2 error is when you fail to reject the null when you should have rejected the null hypothesis. The researcher says there is no difference between groups when there is a real difference. It can be thought of as a false negative study result. The probability of making a type 2 error is called beta. You can remember this by thinking that beta is the second letter in the Greek alphabet. Power is the probability of finding a difference between groups if one truly exists. It is the percentage chance that you will be able to reject the null hypothesis if it is really false. Power can also be thought of as the probability of not making a type 2 error. In equation form, power equals 1 minus beta. It is good for a study to have high power. A cutoff for differentiating high from low power would be roughly 0.8 or 80%. In other words, having a beta less than 20% for a given study is good. Where power comes into play most often is while the study is being designed. Before you even start the study, you may do power calculations based on projections. This way you can tweak the design of the study before you start it and potentially avoid performing an entire study that has really low power since you are unlikely to learn anything. Power increases as you increase sample size because you have more data from which to make a conclusion. Power also increases as the effect size, or actual difference between groups, increases. If you are trying to detect a huge difference between groups, it is a lot easier than detecting a very small difference between groups. Increasing the precision, or decreasing standard deviation, of your results also increases power. If all of the results you have are very similar, it is easier to come to a conclusion than if the results are all over the place. P-value is the probability of obtaining a result at least as extreme as the current one, assuming that the null hypothesis is true. Imagine we did a study comparing a placebo group to a group that received a new blood pressure medication, and the mean blood pressure in the treatment group was 20 millimeters of mercury lower than the placebo group. Assuming the null hypothesis is correct, the p-value is the probability that if we repeated the study, the observed difference between the groups' averages would be at least 20. Now you have probably picked up on the fact that I keep adding the caveat that this definition of p-value only holds true if the null hypothesis is correct, aka if there's no real difference between groups. However, don't let that throw you off. You just assume this is the case in order to perform this test, because we have to start from somewhere. It's not as if you have to prove the null hypothesis is true before you utilize the p-value. The p-value is a measurement to tell us how much the observed data disagrees with the null hypothesis. When the p-value is very small, there is more disagreement of our data with the null hypothesis, and we can begin to consider rejecting the null hypothesis, aka saying there's a real difference between the groups being studied. In other words, when the p-value is very small, our data suggests it is less likely that the groups being studied are the same. Therefore, when the p-value is very low, our data is incompatible with the null hypothesis and we will reject the null hypothesis. When the p-value is high, there's less disagreement between our data and the null hypothesis. In other words, when the p-value is high, it is more likely that the groups being studied are the same. In this scenario, we will likely fail to reject the null hypothesis. You may be wondering what determines whether a p-value is low or high. That is where the selected level of significance, or alpha, comes in. As we have already discussed, alpha is the probability of making a type 1 error, or the probability of incorrectly rejecting the null hypothesis. It is a selected cutoff point that determines whether we consider a p-value acceptably high or low. If our p-value is lower than alpha, we conclude that there is a statistically significant difference between groups. When the p-value is higher than our significance level, we conclude that the observed difference between groups is not statistically significant. Alpha is arbitrarily defined. A 5% level of significance is most commonly used in medicine based only on the consensus of researchers. Using a 5% alpha implies that having a 5% probability of incorrectly rejecting the null hypothesis is acceptable. Therefore, other alphas, such as 10% or 1%, are used in certain scenarios. So here's the key that you need to understand. In most cases in medicine, if the p-value of a study is less than 5%, then there is a statistically significant difference between groups. If the p-value is more than 5%, then there is not a statistically significant difference between groups. There are a couple caveats that complicate things a bit. Both are related to how you can't take statistics out of context to make conclusions. Statistical significance is not the same thing as clinical significance. Clinical significance is the practical importance of the findings. There may be statistically significant differences between two drugs, but the difference is so small that using one over the other is not a big deal. For example, you might show a new blood pressure medication is a statistically significant improvement over an older drug. But if the new drug only lowers blood pressure on average by 1 more millimeter of mercury, it wouldn't have a meaningful impact on outcomes that are important to the patients. It is also often incorrectly stated by students, researchers, review books, etc., that p-value can be used to determine the observed difference between groups is due to chance or random sampling error. In other words, if my p-value is less than alpha, then there is less than a 5% probability that the null hypothesis is true. While this may be easier to understand, and perhaps may even be enough of an understanding to get test questions right, it is a misinterpretation of p-value. For a number of reasons, p-value is a tool that can only help us determine the observed data's level of agreement or disagreement with the null hypothesis, and cannot necessarily be used for a bigger picture discussion about whether our results were caused by random error. The p-value alone cannot answer these larger questions. In order to make larger conclusions about research results, you need to also consider additional factors such as the design of the study and the results of other studies on similar topics. It is possible for a study to have a p-value of less than 0.05, but also be poorly designed and/or disagree with all of the available research on the topic. Statistics cannot be viewed in a vacuum when attempting to make conclusions, and the results of a single study can only cast doubt on the null hypothesis if the assumptions made during the design of the study are true. A simple way to illustrate this is to remember that, by definition, the p-value is calculated using the assumption that the null hypothesis is correct. Therefore, there is no way that the p-value can be used to prove that the alternative hypothesis is true. Another way to show the pitfalls of blindly accepting p-value is to imagine a situation where a researcher flips a coin 5 times and gets 5 heads in a row. If you performed a one-tailed t-test, you would get a p-value of 0.03. Using the standard alpha of 0.05, this result would be deemed statistically significant, and we would reject the null hypothesis. Based solely on this data, our conclusion would be that there is at least a 95% chance on subsequent flips of the coin that heads will show up significantly more often than tails. However, we know that this conclusion is incorrect because the study's sample size was too small, and there is plenty of external data to suggest that coins are fair, meaning given enough flips of the coin, you will get heads about 50% of the time and tails about 50% of the time. In actuality, the chance of the null hypothesis being true is not 3% like we calculated, but is actually 100%. Lastly, we have statistical hypothesis testing, which is how we test the null hypothesis and determine statistical significance. For the USMLE Step 1 Medical Board exam, all you need to know is when to use the different tests. You don't need to know how to actually perform the tests. When you are comparing the mean or average of two groups, you use a t-test. When you are comparing the mean of 3 or more groups, you use an ANOVA test. When you are using categorical variables instead of numerical variables, use a chi-squared test. When using categorical values, rather than having a continuous numerical value that is measured, you have categories such as gender or the presence or absence of a disease. That brings us to the end of the video. I'd like to give a big thanks to Brittany Hale and Dave Carlson for going to my website, stomponstep1.com, and making a donation that helped fund this video. If you found this video useful, please comment below as it really helps me out. And if you'd like to be taken directly to the next video in the series, which will cover confidence intervals, you can click on this black box here if you are watching on a computer. That video will be very much related to this one, so I definitely suggest checking it out. Thank you very much for watching, and good luck with the rest of your studying.